So shall we start the session, sir?
Yeah, yes, ma'am. Yeah, great.
So participants, the current session is about deep learning big data projects using TensorFlow, which will be handled by Mr. Deepan Raj. So let's have a quick intro about our guest speaker. So shall we start the session, sir?
Yes, sir.
So participants, the current
Hello, ma'am. Shall I start the session?
Mr. Deepan Raj completed his Bachelor's of Engineering in Electronics and Communication at Adni College of Technology, and he completed his Master's in VLSI Design and Embedded Systems at Madras Institute of Technology. He worked as research engineer dealing with product research by patterning new technological concepts at Adni Center for Research and Development for about 1.5 years. And he is currently working as an embedded software engineer dealing with Artificial Service Center. He acted as a corporate trainer in various MNCs and also acted as a keynote speaker in various institutions like IIT, MIT, VIT, and many more. He has published more than 5 papers in national and international conferences. And also, some of his notable achievements are: he's been a part of an Indian Book of Records for conducting 700 plus AI workshops on a single day. He also he also appreciate he was also appreciated in person by the former President of India, Dr. APJ Abdul Kalam, for creating a 5-feet cost-effective humanoid robot. He also won the international award. He also an international award winner for contributing a real-time project using robots for easing the work of farmers in the farm fields. He won the international. He also won the another international award for contributing a novel approach in effective brain-computer interface by coining a concept named Neural Linguistic Dictionary. He was also awarded for the most impressive project of the year in IIT Kharagpur for ISRO Mars Rover Challenge. He also won 25 plus technical events in Tech Fest all over India. Now I request Mr. Deepan Raj to take over the session.
Thank you, ma'am. Thank you so much. Yes, ma'am. Am I audible?
Yes, sir, you are audible.
Perfect, ma'am. So,
Okay, sir.
thanks for the kind introduction, ma'am. Good morning, everyone. So today we'll start with this session right away. I believe that Jay Ganesh would have taken about CNN and the applications about it. He's my close friend. I mean, we started a journey in Acme College of Technology, one of the bachelors. So I guess we won't have any gaps in between. I mean, I'll try to, fill in the gaps where Jay Ganesh left. So, as the name implies, today in this session, we are going to focus more about recurrent neural network, rather going for the image-based solutions, which Jay would have taught you. Today, this session, we are going to like travel behind time, travel way before the time, and just understand like how to deal with sequence of data. So that's what it is all about, recurrent neural network. Okay, so we know that for a normal multi-layer perceptron or a CNN, we have a feed-forward network. A feed-forward network in the sense, for example, we get the input data, we process the data using the hidden layers, and we get the output for the same. And we have a backpropagation technique where to, somehow, update the weights so that we get to the right direction. So that is how a feed-forward neural network works. A classic CNN or a multi-layer perceptron will work. But the problem is like the decisions are made onto the current input. For example, whatever input is given to this particular instance, for example, I have 10 data, whatever, if I pass the first data, the output will be correspond to that first data alone. Okay, and the next time if I pass the second data, it will never consider a relationship between the first data and the second data. It will straight away feed the second data and get the output which is actually relevant for the second data, not to the first data. So I can say that there are no memory which is being handled to understand whether any is there any connection between the previous data and the present data. So that is the main drawback of using a feed forward network. Yes, it has its own merits and demerits. Merits in the sense it can do a lot of wonders for images and other stuff. But sometimes when it comes to data like sound or a data that contains some time series, okay, sequence of data that is like that has to be combined together to form some meaning, during that time feed forward network will fail miserably. So that's why we go to this a particular neural network known as recurrent neural network. So the advantage of using a recurrent neural network is like these are the disadvantages showed here. Cannot handle sequential data, consider all the current input, cannot memorize the previous input. So that's what I said the previous slide, right? So it cannot able to handle the previous or the past data and give a connection to the same. So because of that, it lacks memory part. So why we go to this to the technology known as recurrent neural network. So as in this particular block, it defines, right? We have input data. The input data is here, the output data is here. So we are actually having a like a closed loop structure. It's like going again and again and again to understand the entire data onto the same and give us an output. So during this, using this kind of an ideology, we can even handle sequential data. And yes, it will give a connection between the current input and the received input, the previously received inputs. And yes, we have the memory state for the set. So obviously, if I have a word like, for example, A and B, okay. So the first data is given here. Okay, the A is processed here. Okay, the first data is processed as A. Second is given again, B will be processed. So it will understand. Okay, since I got A, B, obviously next can be C or D, something like that, because it is like representing the alphabets. So like this way, I can able to understand what kind of sequence am I getting here. Based on the sequence which is processed here, will be given as an output. So output can be like of any forms. It can be of either many outputs or one output or something like that. We'll see that in detail. But yes, this is the advantage of using a recurrent neural network. So we can go behind time and understand what are the data which is given to that particular thing, and I can able to correlate that previous data with the present data to give some analogy for the set. Like we speak. Okay, for example, if we speak to some person, we don't come to conclusion by just hearing 2 to 3 words. We need to we need to make him finish the entire sentence to understand like what he's trying to say or what he's trying to prove. So that's what recurrent neural network will take care. Okay, so there are like different applications that can be done for recurrent neural network. So one such thing which I can say is the one to many. So one to one, we know that this is just a feed forward. We'll leave it behind. So this one, okay, so one to many. For example, I give an image. Okay, so I give an image as an input. What I want to do is I want to give an output that actually just say what kind of image it is. For example, if a football player is playing a football and a snapshot is taken during that time, okay, if I pass that image to this particular neural network, the neural network should understand what is the sequence or what is the situation which is happening in that particular picture, right? We can do that, right? By seeing the newspaper, by seeing just one image, we know that we know the entire context of what is happening. So similarly, by using one input, just an image, we can even create many outputs like sequence of words. Okay, so that is one area of using neural network. That's known as processing sequence. The second thing which I can say is sentimental analysis. So here in this case, I have multiple words. Okay, like a sentence. The sentence will be given as an input to the neural network. The neural network will process and give me just one output. So this one output is nothing but it's going to be like either a good or bad. Let's say a review, okay, an IMDb review. So during that time, some people would have reviewed it badly. Some say the movie is very, very good. So based on the sentences, the sequence of words which is given there, using that sentence, even we can able to create a sentimental analysis application which can able to say whether the given content is actually saying good about that particular movie or bad about that particular movie. So it applies to all the other sequences as well. Okay, so this can also be done. This can also be taken care using RNN. So many to one is also achievable. And yes, we have came across this particular application way long before. Yes, your language translation. So when you go to Google and you try to translate your words from English to some other language, actually previously, I can say 10 to 15 years back, there were no, RNN or AI sequence which is given there. But now the translation is like very, very perfect, and it's like very impeccable for the other people to understand like what this particular guy is speaking to. For example, from English to Korean, the Korean translation like way more pakka. Even the recent implementation in Facebook, I'm not sure whether you have saw that implementation. Even though we write Tamil in English words, okay, it is being translated to English perfectly in Facebook. So I'm pretty sure that you would have saw that particular implementation. This is like done quite recently. So I can say that this particular application involves many input to the many output. Okay, so I do have many inputs and I'll be getting even many outputs for the same. So sequence of words and output will be sequence of words. And second, the last thing can be like many to many. So it's like video classification. So frame by frame, I will be understanding what it is, and based on that, each and every frame information, I will say that okay, this particular video represent a football scene. This particular scene represents someone beating someone, so something like that, right? So even we can able to achieve this kind of application as well. So using recurrent neural network, it's not only possible to achieve just one to one, okay, but we will not be using one to one for recurrent mostly, because this is like handled using for MLP and CNN. But yes, in this way I can able to achieve one to many, many to one, many to many, and many to many. So I can easily achieve these kind of 4 applications in my day-to-day activities. So it has gained a lot of attention right now. In the recent days, lot of people are inventing chatbot so that the customer service can be automated. Just like that. So people are even trying to achieve that to a greater accuracy, because we know that chatbot is pretty lame, and we even I can say even a dummiest chatbot which we have in a mobile phone, where we try to connect to our customer care. So like an automated voice will be there, it responds to our key presses, right? So it's like very lame, and we directly try to go to the customer care number so that we can talk to the representative right away. But now, in a lot of applications, talking to a chatbot is way more easier than talking to a representative. So it can able to understand these nuances. It can able to understand like what we're trying to convey, so that our request is being taken care way more easily, rather giving information again and again to our customer care. So that's where this RNN got a huge leap. Way before that, people were using this RNN for time series prediction. Even some sound recognition and stuff. But now it has gained a lot of attention for activity recognition and for chatbots. Okay, so I will show you some hands-on programs that can be utilized for creating some good applications for sentiment analysis, and even for some yes or no chatbots. Okay, so let me go to the second slide. Yes, so this is the actual the expression for the recurrent neural network. So you can see this is the new state, h of t. Okay, so this is my function with parameters. Okay, so we'll leave it behind. So this is going to be common, right? So I'm going to leave it behind. So here I'm considering 2 states here. Okay, so the one is the old state, the second is the actual current state. So by combining these 2 things, like old state and the current state, and using some bias information, a function, the parameters, I can arrive to the new state y. So this is how the data are being processed. But in a normal CNN or a neural network, we just focus on the current state, and we add with the function with parameters, and we arrive to the new state. But in this case, we even consider the old state as well. Okay, so to elaborate that particular function, and you can see this weight function will be multiplied with the previous state, and the current weight function will be multiplied to the present state as well. So this function will definitely have a tanh activation function. Okay, so I guess you know about the activation function pretty much, right? But in this case, when people, till now, maybe people would have been referred would have told you that ReLU or Sigmoid are the best activation function which you can ever get for CNN or for a normal neural network. But when it comes to a recurrent neural network, Tanh is the best candidate. So we will see why this Tanh is the best candidate, best activation function for this recurrent neural network later. But yes, I can say that rather going for the ReLU and other activation functions, Tanh termed to be the right function for this recurrent neural network. So I'm expanding this term. This is how your expression will look like on a higher note. So we have a Tanh function, activation function, a weight function multiplied with the previous state, and the weight function is multiplied with the actual state. So based on which the output will be deployed to the final state. So the final output will be given here with a final weight for the same. Okay, so I will give you an idea like how this entire RNN works on a graphical note. So in that way we can able to easily correlate with a normal neural network. Your normal feed-forward neural network with the recurrent neural network, because till now feed-forward neural network is pretty easy to understand, because we pass an input, we pass an weight, we get an output to the next layer, and we pass to the next layer, and we finally get the output, and we back propagate and we update the weight just like that. But in this case, things are little different. Things are little different to to correlate. So let's say I have an input. Okay, h of 0 is the input which I have right now. Okay, this is the previous state input. Okay, this is previous input. This is the present input. Okay, so the weight function which is going to be given is going to be common for all the input passes. Okay, so you can see the entire input is split into sequences here. So for each and every function, the weight will be the same. Okay, so I'm not going to change the weights for each and every input pass. So I'm maintaining common weight function here. So you can see weight is distributed to all the functions. So all I want to do is I just give this previous input and the present input and calculate which has to be passed to the next thing. Okay, so I'll be getting an output known as h1, and this will be passed to the second layer. Okay, so where I'll be processing another input x2. So I'm going to combine this h1 and x2 and get the third one. Likewise, I go along to the number of data which I have. For example, I am a good boy. So I am good boy. So 4 inputs will be there. So like that, I'll be like passing data like in this way and over a common weight. So for each and every input pass, I'll be getting an intermediary output. So that intermediary output will act as the previous state for the current function which you're going to give right now. Okay, so likewise, it goes in this way. And after that, we will be computing output. Okay, so we'll be computing output and the loss function for that particular thing. Okay, so typically the accuracy. So what is the actual loss which we have got for this particular state h1. Okay, so h0 is the previous state. Okay, and h1 is the current state. So we have h1 y1 is similar. So we combine things and we show what is the loss function for this particular candidate. Likewise, we calculate the output and the loss function for each and every state. Okay, so for each and every state, the output and the loss function is calculated in such a way that we can even tap the output wherever we want, which is required. It's not like we want to go for the last part of the sequence to understand the output, because each and every node has an output, so we can tap out wherever necessary for us. Okay, and later on we'll be calculating the entire loss function on a cumulative node. So based on this loss function, I'm going to calculate L1 plus L2 plus L3 plus T divided by the average. Taking an average of this loss function, a cumulative average will give the common loss function for this particular neural network for the particular input data. Okay, so once after that, what happens is like, based on this loss function, the weight will be updated sequentially. Likewise, like for example, based on this loss function, the weight will be updated to each and every terms. Okay, so going backwards, it will update the weights, and finally again the weights will be cumulatively average, and and will be getting the final weight output, and this weight will be fed as the input to the second data pass. Okay, I will repeat it one more time. So we have states. Okay, h0, h1 are the states here. Okay, so this state as contains the previous input and I have the present input. The weight will be maintained commonly for all the input paths. So we'll be having an activation function for the same and we get an output for that. So for that output, we calculate the loss function. Likewise, this current state output will be passed as the previous state input for this function and the current input is also passed. So for that we calculate y2 as an output and we calculate the L2 loss function. Likewise, we go along to the words and we finally, get all the loss function and make a cumulative average for this particular, entire loss function. So using this cumulative average of loss function, we're going to use this loss function to back propagate and update these weights again. And finally, once the weights are updated, again we like take upon these weights and we'll average it again to find the final change of weights. And the next input pass, we're going to use this weight and not this weight. Okay, the individual weight which is calculated will not be used for the next input pass. Only we'll have it, this individual weights will be used to average of the final weight, and that final weight will be used as an input to the next input pass. So this is how a recurrent neural network will have a flow on it. Okay, because when it comes to a normal neural network, nothing will be here, right? The x1, x2, x2 will not be there. So I'm going to give it the data. I'm going to pass every layer by layer, and they're getting an output. I'll like feed forward. Go backward and update the weights. That's it, plain and simple. But in this case, I want to compute the loss function for each and every pass, and I want to even update the weight for each and every pass to get something. So I can say that it is like computationally little intensive when compared to other neural networks, because we do have if the input sequence is very big, for example, if we have an input sequence like more than 40 or 50, then I need to update weight for 50 times and I want to update the loss function for 50 times. So that is a time consuming process. So this is actually the idea behind using the recurrent neural network. That's fine, but what are the problems which we get when it comes to recurrent neural network? So once such problems I can note down is like exploding gradients and vanishing gradients. So I guess you would have got some idea about how does a gradient descendant works, right? I believe so. So using that ideology, sometimes, okay, so let's say I have an input pass. Okay, this input is very useful for me. So my gradient has increased to a huge number. Okay, so just like got a huge leap like this. Okay, like 90% accuracy. The loss function is very less, like maybe like 1% of loss function. So 99% of accuracy, 1% loss function. So the next input pass, since it is already exploded, it will even go to the 100% accuracy just like that, even without understanding what this data does, because since the gradient has reached to a maximum point, that will make a huge problem for the neural network to learn something on its own. So that's one thing. So, and the next thing which I can say is the vanishing gradient. So vanishing gradient is quite opposite, where the where the learning rate will not be there at all, because if the changes of the weights are very less when compared to the previous one. Okay, so if there is no change in weights at all, then obviously I'm not be learning anything from the given data. So these are the two important problem which will be faced when it comes to recurrent network. So in order to somehow discard this exploding gradient, we can have a concept known as truncated back propagation. So truncated back propagation in the sense, what if I update the weights on a batch basis, not to an individual area? What if I take like 2 to 3 batches and update a similar weight, a common weight for the same? That way, I can able to somehow minimize the exploding gradient problem. And yes, it can also be minimalized using the Tanh function, which I will show you in the next coming slide. But this Tanh function will also be used for mitigating this exploding and the vanishing gradients. For both, activation function plays a vital role, and a truncated back propagation will be useful when it comes to problems of handling exploding gradients. And yes, for vanishing gradients, because even exploding gradient can be somehow minimalized, using this truncated back propagation. But vanishing gradients are a little tough, to mitigate. So because of that, we even created another ideology known as LSTM. So long short term memory, or we do have another terminology known as recurrent gate unit. So let's say this meme is like shaking hands with this particular stranger, nice to meet you, and I already forgot your name. So that is how it will be. So I mean, in the instant of time, it will forget the previous state of inputs, and it will never understand like what is the sequence of it, because it just see the past input, not the entire sequence of input, right? For example, if you have 10 data, it will only look upon to the previous data, not to the 10th data, right? So that is a problem, and that's why this vanishing gradient will be a very dangerous, I mean, problem, very dangerous gradient problem. Okay, so we will mitigate it using this I mean, Tanh activation function, and yes, we do have a concept known as LSTM, which I will teach you in the next coming slides. So now here you can see this is an activation function. Okay, without Tanh, I'm just passing the data. Here you can see this 5 is being multiplied, I mean, to a larger number here, right? So the final point is giving me 405. So 405 is like very high. So this in this way, the gradients are very high, so that the learning will reach to a certain threshold, which will not help in the learning rate at all. So it's like going to the top area without learning anything. So that's where, I mean, Tanh is introduced. So when the Tanh is introduced, you can see that the gradient is like, I mean, somehow normalized and like being stayed in 0.9. It's not going above, I mean, even 1. So even initially the value is 5, right? The 5 is being multiplied like this, and we're getting 4 or 5, something like that. But even though when we get an input as 5, I mean, this data, I mean, it's being like somehow normalized and like being maintained inside 0, -1 to +1. So that is the beauty of using a Tanh activation function. So yes. So here you can see this is the actual implementation of Tanh in Sigmoid. So Sigmoid function will have an output varying from 0 to +1. Okay. For Tanh function, we have an input from output which is varying from -1 to +1. So in this way, I mean, going to the value 0, I mean, it is not that easier for this Tanh function, because we want to make sure that, I mean, value is not going to 0 that easily as possible, because it has a secondary partial derivative that will help to, I mean, help this particular data, I mean, to go to 0 on a prolonged time. I mean, if I use a Sigmoid function, the data will go to 0 at some point of time, but it will take a long amount of time for this particular data to reach 0, because it will either go to -1 or to the +1. So using this -1 and +1 as the output, the no matter what kind of data which we get, can be somehow normalized, and it will not explode at all. Even for vanishing gradient, we will mitigate this problem. I mean, rather going to 0, it will go to -1 or +1. So making sure, I mean, the data is becoming nothing. So that's where, I mean, that's why we use a Tanh function for this recurrent neural network. So that's the beauteous point of using this Tanh function, when no one was using this particular guy in normal multi-layer processor or convolution neural network. So I mean, coming back to the LSTM. So this is how it's be. Okay, so let's say, I mean, I'm just purchasing a product in an online platform. So I just see some reviews. So no one will, I mean, read the entire part of the review. So all we need to see is like the star rating for the same, and we'll be seeing that, I mean, what kind of, I mean, important point you have given here. For example, amazing is important to me, right? So amazing is important to me. Perfectly balanced breakfast will definitely be buying it. So if this guy is going to buy again for sure. This box of cereal gave me, so this is not important for me. So I know that this is a box of cereal, so I'm not going to like look upon to this data, as all things should be. Okay, so this is not needed. I only ate half of it. That is also not needed for me. Okay, so these information are not needed at all to me. Okay, so what I do is, when I create, I mean, a normal recurrent neural network, what happens is like, it will first get this data. Okay, amazing. Okay, it will note to the state and will go for the next word, this. Since, I mean, this and amazing is not quality to each other, it will forget this amazing, will go for this. Likewise, it will go to the box, it will forget this guy, it will just look upon this this word. If I go for off, it will forget this I mean, word, and it will go for the box. So only the previous state is memorized. But what if I have a memory unit that can able to load, or that can able to, I mean, hold the important data, I mean, data which is actually required for me to learn something from the data. So in that way, I'm going to discuss these guys. Okay, so as the data passed upon, I'm going to discuss these data, and I'm going to, I mean, store the important data like amazing, perfectly balanced breakfast will definitely be buying it. So only these data will be stored in my memory unit, so that I can give an analogy, I can able to understand what this particular data represents. So I can say with this particular data, I can say this is a positive review. It's not a negative review, it's a positive review. So I can even do some something like that. Even I can suggest some other serials or something like that. Okay, so that's the ideology of using this LSTM rather going for a normal recurrent neural network. So we'll go to the LSTM block right away. Okay, so with this we can straight away go to the hands-on part, because without knowing this, it might be a little difficult for us to proceed to the hands-on area. So so LSTM, as the name implies, it stands for long short-term memory. So it holds the long and the shortest sequences into this memory. So no matter what it is, even long or even it is short, for example, long short in the sense, this memory if it hold for a long time, okay, this is amazing, this is going to be a long memory. If I hold this buying, okay, since the data is already going to finish, this is going to be a short memory, so something like that. So that's the analogy which they are given here. Long short memory is given. So inside the long short term memory, we do have three different gates. Okay, so one gate is known as forget gate, input gate, and the output gate. Okay, so we will discuss about these three gates in detail now. So before going there, you can see, what all the blocks are used here. Okay, so this red block is known as the sigmoid activation function. This is going to be Tanh function, pointwise multiplication, pointwise addition, and vector concatenation. Okay, so wherever you saw a join of vectors together, we're going to say vector concatenation. So as it is noted, like this is going to be the forget gate. Okay, so this is going to be the cell state, and this is going to be the input gate and the output gate. Okay, so let me keep like this. Okay, so it's going to be confusing for us. Okay, so now the input data is coming here. Okay, so the input data is waiting here. I'll be like passing, actually per se, this is where not, this is where my input data is going to occur. Okay, so I'm not going to get anything here, because it's going to like go to the previous data. This is going to be the previous data, this is going to be the current data. Data is going to come here. Okay, here I have this Tanh function here. So Tanh function will decide, okay, because I can if I have a coefficient of 0, okay, I can say that previous data which is going here can be multiplied, can be eliminated as 0, because 0, when I give input as 0 to sigmoid, it will definitely discard the value to 0. So this gate will act as a forget gate, which will allow me to forget the previous data. So if I feel like this data is not useful for me, I'm not going to store this guy to the next level. So I'm going to use the forget gate to remove that particular thing. And after that, we'll be going to the input gate, where sigmoid functions also used, Tanh functions also used. So sigmoid function will decide, okay, whether the previous state can be given here. If it is like 1 to be given, this will be 1. When multiply with this particular sigmoid, I'm going to pass down the entire data to here. And yes, Tanh function will be here. That will help us to normalize the data. Okay, since we don't want to deal with the exploding or the vanishing gradient, we use Tanh function to normalize the data, and we pointwise multiply it, and we pointwise add it with the cell state. So now, this particular data will be like perfectly balanced here, because we know what data to be like passed to the next layer, and the unwanted data is like going to the forget gate, so that the data will be like eliminated. So input gate will understand, okay, this data is very important. I'm going to like pass this guy, and I'm going to normalize it, and I got it in the cell state. And finally, I'm going to pass this guy here. Okay, so it's again going to be normalized, and again I'm going to like understand whether this has to be passed to the output gate, that can be like that can go to the next layer or not. Okay, so based on that, I'm going to give either 0 or 1. If I give 0, this is not going to be passed to the output area at all. It's going to stay here. Okay, if not, if I give 1, it's going to the next area. I'm going to pointwise multiply it, and I'm going to give it to the next state. So this is how an LSTM will work. This is how it look like. So with using this 3 gates, forget, input, and output gate, I can able to memorize some important data, and even discard some unwanted data into the memory. So as a name implies, it's like a memory unit. So each and every block will be having some memory unit to hold some particular data for this, like your flip-flop or something like that. Okay, so and yes, we do have another different ideology known as gated recurrent unit. we will see that a little later. But anyways, yes, okay, we'll see this as well. So we'll finish everything at one shot and go for the answer title. So anyways, LSTM is given here. So in gated recurrent, it is also similar to LSTM, but yes, I mean, rather having three different gate, I mean, we like restrict it to 2 gates. Okay, so okay, there are some chats. Okay. Yes, as I was saying, I mean, this reset gate will be responsible to discard the unwanted data like the forget gate, and even this update gate will be a combination of input gate and the forget gate, where it will understand, okay, the current state have to be forget, have to be removed, or not have to be removed. That can be passed to the next state or not. So it's like somewhat similar to the LSTM, but gated recurrent unit serves to be somehow the best. I mean, thing when we compare to the LSTM, data, because since it has some simplified gate logic, it can able to hold large amount of data, and you can able to easily, get a good accuracy than LSTM. So we will deal that later. And now, let me like give you a small ideology about how does an NLP work, because without knowing this, we cannot able to understand the input data. Okay, so I'm going to give you a small ideology, because you know that when it comes to images, we have this pixel data with us, and we like somehow vectorize it way more easily. But when it comes to word, we don't have numerical representation for that particular word. Okay, so we need to somehow vectorize the data in a way that all the words are being converted to a number. Okay, without converting into a number, we can't do some application with the neural network or something like that. Okay, so here you can see for each and every character in the beginning of time, people created vectors, some numbers for each and every character. But this seems to be like somehow exhaustive, because a lot of numbers are there, and that will make some confusion. For example, here you can see silent and listen is somehow having the same words here. Okay, so if I combine these guys together, I can say like all the numbers present here will also be present here. So we cannot give some meaning to whether this is the same word or a different word. Okay, so that's where people stop this kind of a thing, and they like go for word based encodings rather having some character based encoding. People went for word based encoding, where I'm going to find some unique words for each and every word. I'm going to give some vector for this. And here you can see the first word is I, so it is given as 001. The second word is going to be love, it's going to be 002. Third is going to be my, and fourth is going to be dog. So 001, 002, 003, and 004. So for each and every new word which is occurring to the sentence, I'm going to vectorize it, word by using some numbers. So here you can see I have 2 sentences here. The first sentence which I have here is I love my dog. So where you can see 001, 002, 003, and 004. The second sentence, I do have I love my. So it is already been there into my sentence, and I've already vectorized for the sentence. So 1, 2, 3 is already present. But cat is a new word for me. So in order to since I know that this particular cat is a new word, I'm going to assign a separate word, a separate number for it. Likewise, I'm going to encode each and every unique word to a different number, so that the entire sentence or the entire data set can be vectorized to the way that these numbers can be given as an input to our neural network. Okay, so there are like different techniques that can be attained to even reduce the effort which is required to learn something like sentence-sized lemmatization, stop words, parts of speech, dependency pattern, word. So I will like cut short very shortly about this. Sentences is nothing about finding the number of sentences. Okay, if I have 3 to 4 sentences, this sentences will be like useful to understand how many sentences are there. Lemmatization is something like, for example, if I have a word run, okay, runs, running, and runner. Okay, so I can say that run, runs, and running are actually giving me the same meaning, right? It maybe like gives the past or the previous state, but I'm not going to do that. I'm just going to define the action. So these 3 action is going to say it's going to describe the same action known as run. So I'm going to convert these 3 guys into single word known as run, rather having 3 different words for it. But this runner is different because it's like actually representing to that particular candidate who's running. So it's going to be it's going to be a different word for the same. Okay, so I'm not going to like commonize with this guy, but yes, if I have some commodities that actually represent the same action, I'm going to combine this guy into a single word rather than having 3 words for the same. Likewise, stop words, some stop words like exclamatory mark or some unwanted words which is actually not needed. For example, the is not needed at all, right? Maybe on a grammatical note, the is will be like useful, but sometimes this might be like not actually contribute to the meaning of the particular sentence. Likewise, parts of speech to understand what is word, a verb, or a noun, or a pronoun, or an object, or something like that. That can also be sometimes used. A dependency parsing, like what is a dependent data, which is like for example, verb is dependent on a noun is dependent on a pronoun, something like that, right? So that is also can be done. And as word work is something like which I've told you right now. So converting your word into a vector. So as I told you, as I given in the previous slide, so like 1, 2, 3, this is known as a word vector. Okay, so like encoding something like on its own. So this is what I want to convey in the theoretical part. So let me like go to the hands-on right away. So there are a lot of chats here. Okay, so there is a question. I can't seem to understand like the question. Is it related to the question or to the attendance? Okay, anyways, we'll give you the Q&A in the final part of the session. So let me go to the Google Colab. Okay, so that's where we're gonna like do some hands-on. Gonna type Google Colab. Okay, so I guess you would have some hands-on session with Jay Ganesh. So I'm gonna like cut short to that particular point. I'm going to go to the GitHub area. I'm going to type Deepan Raj M. This is going to be my this is my repository in GitHub. Okay, I'm going to search for that. So I do have different repositories here. So go to deep learning. So inside deep learning, you can find, NLP/NLP.ipython notebook. So let me zoom it out a little. So go to Deepan Raj M, go to the GitHub tab, go to Deepan Raj M, go to this particular repository deep learning. Okay, so where you can see a particular IPython notebook as NLP/NLP.ipython notebook. So I'm going to open this one, and I'm going to show you like how to use a small data. Okay, so yes, using the data, how can I like create this sequence of sentences? Find this sequence and giving some word vector for the same. Okay, so here you can see I've imported a library known as TensorFlow, inside which we have Keras for the same. So we're going to use TensorFlow library, inside which we have a Keras library which is actually embedded right now, because TensorFlow and Keras like somehow combined together in the recent version. So I'm going to use Keras, which is actually inside inside TensorFlow. Okay, so so a lot of chats. Perfect. So I'm just creating a sentence here. Okay, so a sentence is like, I love my dog, I love my cat, you love my dog, and do you think my dog is amazing? So this is my sentence. Okay, so once I got the sentence, I'm going to tokenize it. So tokenize is like, each and every word is going to like act as a tokenizer. Okay, so I'm not going to look up onto the chats. Okay, let me forget the chat right now. So using these sentences, for each and every word, I'm going to fit some indexes for the thing. So here you can see tokenizer.fit on text to the sentences. So I'm just initializing the tokenizer function here into this particular object, and this object is going to perform the action for the same, where I can able to fit each and every token of this particular sentence. So fit on text sentence. So and finally, I'm going to give an index for the same. Okay, so index is going to be something like this. For example, my is going to be 1, love is going to be 2, dog 3, I 4, you 5, cat, something like this. So for all the words, for all the unique words, I have given some numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 unique words are there inside this particular sentence. I've given 10 numbers for the same. And yes, sometimes we need to pad up the sequence. When I this is just for one sentence. And if I have multiple sentences, I want to somehow pad up the sequence, right? Making sure all the data is like somehow aligned together. For example, if I have in one sentence I have 10 words, in another sentence I have only 5 words. So during that kind of a time, maybe I can even add some zero padding at the end or to the beginning, so that all the words will be in the form of 10 10 numbers. Okay, so that's what I'm going to do here. So as usual, I love my dog, everything is given here. And another thing which I'm going to do is like out of vector. Okay, so I'm going to initialize the tokenizer with another parameter known as OOV token. So out of vector is something like, for example, okay, this is inside my dictionary. Okay, so I have already stored this particular data and I assigned some number for it. What if my input data or my query data that doesn't have a word which is actually inside this particular sentence? During that time, this OOV will be taken care of. So if I have a word that is not at all used in the sentences, okay, that is going to be termed to be 1. Okay, if I have a different word, for example, maybe a lion. If I give an input query as a lion, definitely lion is not there in the sentence. So I'm going to queue number 1 to that particular line word. Okay, so maybe let me run this particular part now. Okay, I'm going to run it away just like this. So make sure that we have a GitHub account and a Google account for this to happen. So it might take some time to connect and to initialize. Once that is done, we are good to go. Yes, it is connected, and I'm just trying to run this particular guy. Yes, the output is got. So I'm just giving this sequence again. So here you can see, OOV is fitted out. I'm going to tokenize again. I'm going to view the word index, and now I'm going to find the sequences. Okay, so because it's like a form of a sequence. So for each and every sentence, for example, I love my is a sequence. I love my cat is another sequence. You love my dog is a sequence, and 4 sequences is going to be, do you think my dog is amazing? So we do 4 sequences. So I'm going to like make a sequence for the same. Okay, so sequences will have the sequences, and I'm going to give a particular I'm going to pad this with a max length of 5. So no matter what my sequence can be, I'm going to consider only 5 numbers for the same. If it is lesser, I'm going to pad it up. If it is not less, if it is greater than the number 5, I'm going to eliminate the guys who is coming after that. Okay, so that's how we are going to do right here. So I'm going to print the word index. Okay, so let me run this particular part. So we'll be getting 3 outputs here. So first thing is going to be the word index, which you can see. OOV is considered to be 1, and the rest of the words has been given some vectors. Okay, if we have some unknown words, that will be considered as 1. Okay, the second thing is going to be sequences. So for the first sentence, it's this sequence. Second sentence, third sentence, and to the fourth sentence. So here you can see the first 3 sentences are some more four numbers are there, but for the final sentence, it's like some more bigger. So obviously the pad sequence is going to be 5. So on default node, it's going to be pre-padding, so it will not be post padding. Okay, so since the pre-padding is mentioned, I have only 4 data. So 0 will be padded in the previous word. Okay, so before the sentence, I'm going to pad a 0 value and then give this particular value. So you can see the final padded output here. Okay, padded sequence output here. So 5324 is there. Since the maximum is going to be 5, I'm going to add a 0. Likewise for the second sentence, for the third sentence. But for the final sentence, okay, I do have I have seven numbers here. Okay, because of this, I will remove this first 2 things, because since it's padding sequence, okay, so since this first 2 numbers are not required, because since I'm going to pad the pre-pad it, I'm going to consider the last 5 numbers alone. Okay, discarding this 8 and 6. That's what is given here. So 9, 2, 4, 10, and 11. So making sure all these sequences have the same length. That's how the neural network will work, right? Because if you have a different length of sequences, a different length of data, definitely it will throw you a lot of errors. So we need to make sure that all these sequences are somehow the same. Okay, so that's what I've done here. So now I'm going to give a test data here. Okay, here you can see I really love my dog. My dog loves my house much. So obviously, here you can see really is a new word here, right? And house is also another word, another new word. Even much is a new word. So I'm going to understand how things work for my particular tokenizer test data. Okay, so that's what I'm going to print here. So first I'm just giving a sequence here. Like this is going to be the sequence. So 5 1 3 2 4 2 4 1 2 1 1. So because my is number 2, house is going to be 1, much is going to be 1, because this is like out of vector. House and much is going to be out of vector. Even really is going to be out of vector. That's why 1 is given here. but for the known things, I mean, you can see the same word, same numbers given. For I is this 5, right? So here you can see for I it is 5. Likewise, really is out of vectors, I'm going to assign 1. Love is going to be 3, my is going to be 2, and dog is going to be 4. That's what is given here, right? So 5, 1, 3 to 4. Likewise, 2, 4, 1, 2, 1, 1. So since I mean, in this case, I'm just, giving max length to be 10. So you can even give pre-padding and post-padding. So it's better to maintain the pre-padding sentences, because the initial point, if it is 0, nothing harmful with it, but at the ending point, if it is 0, it might contribute something different, because 0 1 is going to be 1 and 1 0 is going to be entirely different, right? So that's why we mostly go for pre-padding. So you can see, since I've given 10 as the pre-padding length, so a lot of zeros are appended here, like 4 zeros, and for this case, 5 zeros are appended for the first sequence, 4 zeros have been appended to the second sequence. Okay, so if I try to run this particular piece of code, this is what I'm going to get. So this is just to, just to make you understand how does a neural network, a normal NLP, how do you create feature vectors for an NLP data? So that's what is given here. This is not that important, because we do have different methods to do that. But yes, this is also a mandatory step which you want to do, because we are doing this pre-processing step. We are converting the words into a feature vector by using the TensorFlow, but not using other libraries. Okay, so I'm going to open a notebook, another notebook here. Okay, Deepan Raj M. Okay, so as I told you, I'm going to look for NLP and sarcasm. Okay, so I'm going to download a dataset known as sarcasm. Okay, so sarcasm, as the name implies, this particular dataset contains some headings of the news. Okay, based on the headline, we need to say whether this particular news is actually sarcastic or not sarcastic. So you can, I can say one example.
Participants, you are requested to kindly mute your mic. Kadirvel sir. Kadirvel sir, can you please mute your mic?
Bye. Bye bye.
Deepan sir, can you please mute him? You are the host now.
Okay.
Bye bye.
Okay, great. Sorry for the disturbance. So anyways, here you can see, I'm just, let me open this particular link. Okay, so that I'm just trying to, when I show this particular link, you can see this is how the data look like. So I have an article link. It's everything is a form of JSON file actually. So article link is given here. That's one input. Headline is given here. Okay, and it is showing whether it is actually sarcastic or not. And finally, the final thing is article link. So we're not going to take care about this article link and the, we're not going to take care about the article link. We're going to look for the headline and the actual output. So this is going to be the input. Okay, headline is going to be the input, and sarcastic is going to be the output. So you can see farmer wet say store clerk shoes over secret black coat for minority shoppers. So it is not sarcastic, it is actually real. So let me take okay, this might that really takes the mood off. Fine. So let us understand this particular headline. Okay, mom starting to fear son's web series closet thing. She will have 2 grandchild. So this is actually sarcastic. So it is not actually meaning to this particular headline. They are sarcastically, meaning some, giving some other meaning to this particular headline. Likewise, even Donald Trump says people to inject sanitizer into their body. So that is actually sarcastic, but people thought it is actually not sarcastic and even blamed Donald Trump for it. So that's what we're going to do. So understanding a sarcastic headline, understanding a sarcastic meaning is even tough for human beings, right? I know that. Sometimes people don't get some sarcastic jokes. So, but yes, we are going to try to make this sarcastic knowledge, we're going to embed the sarcastic neuron to our neural network. So the first example which I'm going to show you, we are going to use a normal multi-layer perceptron. Okay, so because I want to like show you the differences, like why we are going to go for recurrent based neural network. Okay, but anyways, I'm going to import the JSON file. Okay, a JSON library which is going to load down this particular JSON. By using this wcat, I can able to download the particular data to my local directory. Okay, so that's what is given here. And then I just open the JSON file and I load the entire data set. So data set contains three things, right? One is sentence, label, and URL. I'm not going to care about the URL now. I'm going to care about the sentence and the labels. Sentence is going to be the input, label is going to be the output for the set. Okay, so sentences dot append item dot headline. So I'm going to append everything to the sentences array. Your list, labels, and the URL list. Okay, so now entire content, entire input content is stored. Come on, guys. Too bad. But anyways, okay. So here you can see just converted my input data into a list that contains the entire input data and the entire output labels for the same. Okay, so again here you can see I just imported this tokenizer library and the pad sequence libraries. Just to make sure we need to convert this data into tokens, right? Because former there will be like a lot of words here, a lot of big vocabulary set is there. So obviously we need to tokenize each and every word for the same. Okay, that's what I'm going to do here. Okay, so I'm going to tokenize it and I'm going to pad it up. So I'm going to do the post padding here to show you something different. Okay, so for padding is going to be post, and I haven't mentioned the maximum length of sequence, right? You can see the max length is not given yet. So what happens is like it will take the average of the max length, average of the sentences, average length of the sentence, making sure which can be the average length for this. So I just given the factor to the data itself, to the library itself to handle that. Okay, so I'm going to padded everything. So this padded is going to be the actual sequence for this. And now I'm going to create a normal multi-layer perceptron. For that, I just import the sequential and dense data, dense objects, the functions. So as usual, you know that model is equal to sequential. I'm going to initialize the model, and I'm going to add 40 data here, 40 input neuron, because I printed here. Okay, let me run this part first. The first block. So this first block will show you like what is actually happening inside, rather going for the next sequences. So you can see it is downloaded, right? So the data, you can see it here. Sarcasm.json is loaded here, and these many unique words are there. 29,657 data are present here. Okay, so that's what I printed here. You can see print length of word index and print the entire word index. This is the entire word index which you can see here. Okay, 29,657. And finally, I just print one sequence. So this is how the first sequence will look like. Okay, so 308, 15,115, something like that. But sentence is very small, so rest have been added to zeros. So here you can see I have 26,709 data. For each and every data, I have 40 as the length. Okay, so because the max length is turned to be 40, because based on the average which is taken for each and every sentence, it is decided to have 40 as the max length. Okay, so why I'm using this 40 as the input neuron. Okay, so the input layer will have 40 neurons. Okay, so we'll have 40 neurons to accept each and every data. Okay, and then the second hidden layer is going to again have 40 neurons. Okay, so the init function is going to be uniform. The activation is going to be redo activation function. So the first layer is 40 input layer. The second layer is 40. It is going to be the hidden layer. Again, the third layer is going to be 20 hidden neurons. Okay, and finally I have only one neuron that is going to give either yes or no, whether the given data is sarcastic or not. Okay, because we're going to find whether the given data is sarcastic or not, right? So I just give only one neuron. So 40 is the input data which is going to be accepted. Hidden layer 40 and another hidden layer is to be 20. Okay, so that's given. And finally, I'm going to compile it. Okay, I'm going to find the loss function, which is the binary cross entropy, the same technique which you would have used in the previous session. Optimizer is going to be Adam. There's no differences. Epoch is going to be 200. Batches is going to be 100. Okay, so 100 is pretty good. I mean, even you can increase the batch size to increase the speed of execution. But yes, I'm going to stick with 100 here. Maybe let me reduce to 100 epochs. I'm going to go for 200 epochs here. Okay, so I'm going to finally print this core matrix for the set. So let me first import the contents and stuffs. Oops. Okay. Yes. So we need to one extra add up here. I mean, since in Google Colab, your Keras is, I mean, update to a latest version, but the code which I've used, I mean, the Keras is to an older version. So I mean, we are getting this problem. So I need to install pip install Keras is equal to 2.1.2, rather 2.4.1 is 2.1.2. So let me install it, and then things will go pretty easy. Okay, now restart the runtime. Yes, we need to restart it. There's no other way to go. We need to load the data again because okay, we do have the data. So, but anyways, we need to load to get the sequence for the same. It's done, and then I'm going to import the library. Let me delete everything. 1 second. Okay, one minute. So let me do it. Okay, this is Keras 2.1.2. I'm just confirming it. So I'm going to import it. This is strange. Okay, now I got it. So we need to uninstall Keras as well. I mean, TensorFlow as well. This might take some little time. Please do bear with me. Pip uninstall. Yeah, I mean TensorFlow, because TensorFlow is upgraded to 2.0 right now. Okay, because of which we are getting this problem. So I'm going to use TensorFlow 1.14 for this particular program. Okay, so I'm just installing 2.1.2 and TensorFlow 1.14. Okay, so it is installing. It takes a little time to do that. It is done. Yep. Restart the runtime one last time. Now things are going to be pretty normal. Okay, so the local variables to update done. I'm going to import Keras. I'm going to load the model. I'm going to compile it. If you can see the accuracy which I'm getting for each and every epoch, it's like close to 59, 60 the maximum. Okay, you can see the speed of speed at which updates the data for one epoch, right? Because like very fast, even though we have 26,000 data with us. I mean, since I'm using a normal multi-layer perceptron, I mean, it doesn't have to, I mean, store the sequence or to update the weights for each individual input. So it's going to consider everything on a whole basis, and it's going to like that provide one time for one epoch. So that's pretty easy to do that, right? So even batch size is 100. So for only for 100 data, I'm going to like update the weights for the same. So I can see the final accuracy for the multi-layer perceptron is like 63.10. Okay, let me go for another code. Okay, So that is going to do the same operation, but this time I'm going to use the LSTM architecture. Okay, rather going for the multi-layer perceptron, I'm going to go for the LSTM architecture. So everything is going to be the same here. So there will be like no difference still in this particular block. So let me run this particular area right away. But we need to make sure that, okay, oops, I need to stop this because we need to again, this is a new runtime, right? So we need to make sure we are uninstalling Keras TensorFlow. This is a little problem when we are going to use Google Colab. Version control is not there for libraries because Google Colab will automatically update to the latest libraries. So when we are going to create some code, we need to try to adapt to the latest libraries as well. Because which it was showing error to me, right? The previous version, the function was working fine, but in the latest version, they would have removed that particular function to a different name. So whereas, so you can note it down like 2.1.2 will work better for this particular code. TensorFlow is going to be 1.14. Okay, but yes, I mean we're going to like we're going to like oops, we're going to use double equal to. So it's always better to go for TensorFlow 2 because inside which we even have Keras. So make sure to migrate the same code which I have to the latest version in the upcoming days. I'll guarantee you that. Yes, it's almost done. So this is the problem which you will get while running some code. Even though, you might be thinking the code is right, but it might throw you some errors. It's all because to the version mapping. Your code might be working in the old version, but sometime your code might not be working in a different version. So that's one thing you need to take care. Yes, restarting runtime. I'm gonna run this particular guy just like that as usual. So everything is going to be the same. So there will be like no problem for me. So now here you can see I have added two more libraries here. Okay, so LSTM and embedding. Okay, so that's the new guys who's like entering the area. So here you can see I have created a layer that is doing this embedding operation where these are like two things. I'm going to accept 30,000 data. Okay, 30,000 sequences that is going to have a length of 64 words. Okay, because for every sentence I have 64 sorry, I'm just confusing you guys. 64 is going to be the embedding bit. Okay, so I'm going to convert each and every data into a 64-bit data. Okay, each and every word to a 64-bit data. So that's what this embedding does. So I'm going to expect 30,000 sequences for the same. The input length is going to be 40, and I'm dropping out some data here. In the previous example, we didn't do any dropouts here, but here in this case, I'm going to drop it out because I have a lot of data here. 30,000, close to 30,000 data are there, right? So I'm just dropping out 20% of data to make sure there's no confusion. And after that, I'm going to use an LSTM block that has 40 LSTM blocks. So 40 memory units are being introduced to this particular area because I'm just trying to match up with the input length so that things might be a little smoother and things might be a little accurate. Okay, so and final layer is going to be one output neuron that's going to be giving yes or no. Input is initialization function is going to be uniform, activation is going to be sigmoid. Okay, because only for LSTM block we will be using this Tanh function, but for the output, yes, we need to use sigmoid function because that will give us 0 or 1. Okay, so because everything internally will be like handled when we call this LSTM blocks, so we don't want to worry about it. Okay, so I'm just going to run it out, and yes, here you can see loss function is the same, binary cross entropy optimizer is also the same, but I'm just making sure epoch is just 1. Okay, because let me change it to 5 here because it will be like very slower because as you know that the updation policy of this thing is like very time consuming, right? Here you can see for one epoch it is taking this much amount of time, but in multi-layer perceptron it's like very easy because it's not computationally intensive. But in this case we need to update weights for each and every data and even update the loss function for each and every input pass, so why it is taking much time. So you can see for the first epoch I'm getting some accuracy close to 69, which is actually higher than the multi-layer perceptron 100 epoch output, right? So for the second epoch, I'm getting, okay, someone is trying to draw. Wait. So for the second epoch, I'm just getting an accuracy of 75. For the third epoch, I'm just getting an accuracy which is like close to 80. So you can see, I mean, and the epoch increases, the accuracy is like going very, very higher, right? That is the beauty of, I mean, LSTM, because it is storing the important data which is required. So as the epoch increases, it can even give us a better output, because storing data has already been done. So it knows what data to be stored and what data to be discarded. Using that data, it can able to easily, I mean, identify whether the given input is sarcastic or not. So 84%, yes, 87. For the fifth epoch, I'm getting an accuracy which is actually closer to 88, I believe. Let me see. Let us check with the actual accuracy in a minute. Maybe probably in some seconds. So you can see for each and every input epoch, it took like 90 to 18 seconds for one epoch. So the final score which I'm going to calculate for this thing is going to be 88.92%. So it is a huge leap, right? For multi-layer perceptron, we got 63%. For LSTM, we got 88%, which is actually quite good. So maybe, I mean, let me try to do the same thing with the GRU. Okay, the gated recurrent unit. Rather going for LSTM, I'm going to go for gated recurrent unique. So, I mean, I've recently added this particular guy. So we don't want to, I mean, change the TensorFlow and Keras version. You can run it directly. Okay, so run this particular guy as usual, the same piece of code. But in this case, you can see everything is the same here, right? I mean, only thing which I'm adding here is like this particular guy, GRU of 32. Okay, so I'm going to add 32, I mean, gated unit, not 40. 32 is maintained here. So, and even one layer is removed and the final layer, like just like the LSTM, I'm making sure, I mean, everything is like mapped to the same 64-bit, I mean, encoding. And then 30,000 input output expectancy and input limit is going to be 40. Only difference which I'm making is gated units like 32. Even I'm making it way more lesser than the LSTM. And let's see like whether it is actually outperforming LSTM or not. Okay, so I'm going to run this guy. Okay. So this is going to give me the output for the same. So, oops, I just given as one epoch. Sorry for that. But you can see, I mean, the first epoch for LSTM, it was just 65, right? I mean, 69 something. But you can see even in the first epoch, I'm getting 79. So maybe let me turn it to 5 epochs. So things might be even much better. But as you can see, it directly jumped to 93% because already the variables which is holding the values, which is actually there. So one epoch is already being considered. So that's the thing which you want to take. But anyways, let me run this particular block fully. So it's like clearly outperforming LSTM, right? So I do say that when your input sequence and when your data set is very, very high, it is always better to go for gated recurring unit. But sometimes, I mean, if you like feel like, I mean, the input data is like somewhat lesser, and that time you can even switch to LSTM because it has 3 different gate units that can able to combine things like more easily. But yes, sometimes it is always optimized things with lesser data, and it's like somewhat faster than the LSTM. I mean, you can see the time required is just 16 seconds, but for LSTM it took like 18 to 19 seconds, right? So that is like, I can say, because of the input gates. Two gates are there for GRU and 3 gates are there for the I mean, LSTM. Okay, so it's running. So it is already reached to the accuracy 99, like close to 100, right? So I can say it's like doing the best thing here. Even it can outperform human being, right? When even us, I mean, I can say that we can't even achieve 100% accuracy for all the persons to understand some sarcastic meanings. So that is where, I mean, I can say that GRU somehow outperform LSTM when it comes to a huge number of data set. Okay. So let me go to the final part. I'll cut short things to just 5 minutes. We don't have much time here. Okay, so give me 5 minutes. I'll finish it out. I just want to show you another, I mean, implementation known as attention model, which is similar to LSTM. But yes, I mean, this is going to be an yes or no chatbot. Okay, so I'm not going to go into details. So what we are doing here is like, we're just having some sequence of data. Okay, so let me show you the data set. So the data set contains question, a sentence. Based on the sentence, it's going to give me some question. Okay, and it's going to give some answers. So I'm going to run everything just like that. I'm pretty sure that this won't give me any problems. I'm just cloning the data here because I have a data set which is inside the GitHub repository. So I'm just cloning to get that particular thing. So inside attention model. So I have some text files here like test and train. So let me download it to show you like how it is really. Perfect. So this is how the dataset will look like. Let me show you that. Oops, the format is not right here. Maybe let me show it here itself. So this is how the data will look like. Okay, so this is going to be the sentence. Okay, Sandra went back to hallway. Sandra moved to the office. This is going to be the sentence, and this is going to be the question. Okay, is Sandra in the office? So for that, my chatbot should say whether yes or no. So it's like a sentence will be given to the chatbot. Based on the sentence, we can ask any question to the chatbot. The chatbot will say either yes or no. So that implementation is given here. You can give it a look. Okay, it's in my GitHub repository. Okay, so I can show you the final output. How it is like been tested. Okay, so the question is, you can see my story. I just created a story like Sandra picked up a milk, Mary traveled left. Okay, so my question is Sandra got the milk. So what output should it give? It is giving me yes. So actually Sandra picked up the milk. Yes, obviously she picked up the milk. So Sandra has got the milk for sure, right? So it is giving me the answer is, but you can see the prediction accuracy is 50% because it's not sure with that the particular sentence and thing, because it says she just picked up the milk and no one gave it to her. So she got the milk by herself. So some relevant question is missing here, because of which the accuracy is little less. Because even we will be not sure whether she have got it or someone gave it to her, right? So there's a huge difference between the language with the verbs and to the grammar, right? So because of which I'm getting a lower accuracy. But yes, this is also a newest idea which is recently implemented. I can also share you this particular a paper. This implementation is done based on the paper actually. So I can share you the paper as well. Attention model. Using that paper, I have done this particular implementation that can able to give a yes or no answers for the same. Pretty much that's it from my end, I can say. So now you can unmute yourself and you can talk and you can ask for doubts if there are any. Okay, so a lot of questions on the test and the certificates, but yes, do we have any other questions, like any technical questions? Now's the time. If not, we can end up the session right away. If people are very interested on getting the yes, and I will share you the code link. You can go to the GitHub repository, www.github.com/Deepanrajyan. Let me share it to you in the chat box. Yes, so this is going to be the link. Okay, so you can get all the contents here. So I do have different repositories here. So inside deep learning, you can see all the contents. Even the content which Jaganesh took is also like available here. So CNN, mask card, CNN, like object detection, a lot of things are there. So you can also take a look onto it. So you can get my email ID This is my email ID. If you want my contact details, this is my contact details. You can also visit my website to get all the relevant information. www.deepanrajn. Yes, so .in. So pretty much you can get it from here. So if you have any other doubts, if you have any other clarification that has to be made for the codes or the content which is in my GitHub or to the current thing, you can always ping me in WhatsApp, and you can even mail me for further discussions. Okay, so I hope this session is useful, but please do make sure you practice these things in your Google Colab, because you don't want to set up anything, because everything is there in the GitHub. You just want to import the files and you want to run it out. So you can go line by line to understand what is actually happening there. And yes, there is a huge documentation for TensorFlow. So once you go for TensorFlow docs documentation, so the entire guide, the entire things for the TensorFlow is actually given here. So you can get all the relevant information for the function which I've used here. Okay, so that's another thing which you can do. But yes, if you can't able to understand like some particular line or a piece of code, you can always WhatsApp me or mail me to onto your outputs or to your query. So great. Any other questions or any other doubts which you want to clarify? Because this is little different from the normal neural network information, because for all the neural networks it's pretty different, but RNN is like somehow very different to understand it. So why, please do give it a look.
Thank you very much, Deepan, for sharing your knowledge. Participants, if you have any queries, you can type in chat box so that our session speaker will address. We will give 2 minutes time for query. Okay, since there are no queries, we shall end the session. Deepan sir, thank you very much for sharing your valuable knowledge regarding tensor and deep learning. And we have some questions, sir. Whether RNN is suitable for image classification?
Yes, Yogapriya. So I can say that RNN can be used to understand some sequence of images, but for image classification, CNN is the best, because you can get a lot of important details in an image using CNN by using some other filters which you can use. So that's where it is a particular area where CNN is introduced actually, for particularly for images. But yes, you can use RNN combined to CNN to do some sequence classification. So yes, it is possible to combine CNN and RNN. So what you can do is you use a CNN to classify things, and you use an RNN to understand to get some meaning with the actual classification done for each and every frame. So that way we can able to understand the sequence of the video. Yes, autoencoder, yes, you can also do that. So actually CNN, as the name implies, everything it's inside the autoencoder. Autoencoder is like something like you're going to use a CNN architecture, just like that, but you're going to use some decoding mechanism to decode that particular your convolved value to another output. So yes, actually it is a CNN. So it's not you're going to combine CNN with autoencoder. You're going to autoencoder is actually a CNN family. So there's no combining things up.
Okay, any more questions?
Thank you.
Yeah, thank you. Deepan sir, we would like to thank you for your informative session, and especially for adjusting the schedule. We have to thank you and Jay for taking over the session in the morning. Special thanks from VCET to you.
Thank you, ma'am.
Thank you, sir. Shall we leave now?
Yeah, yes. Thank you,
Thank you.
everyone.
Thank you
for
so
the
much.
opportunity.
Yeah, thank you.
Thank you, ma'am. Bye-bye.
Participants, you will receive feedback link now. You can fill up the link. Bhaskar sir, test will start once the feedback is over. Feedback link is shared in the chat box. Participants, kindly fill your feedback. Mm. Mm, mm. Test link will be available from 1:10 p.m. Information to all participants. You will receive test link sharply at 1:10. Thank you, Charu ma'am, for submitting the feedback. You can wait for a few seconds so that you will receive the test link. We shall wait for all participants to complete their feedback. Devendran sir, you will receive the test link sharply at 1:10. I thank all participants, those who have submitted the feedback. I am getting replies from chat box. Thank you. Thank you, Bhaskar sir, for your appreciation. Thank you. Senthil sir, we don't have session in the afternoon. Once the test is over, we will complete the sttp. Shivakumar sir, test will be at 1:10. Bhaskar sir, as we told in the voucher, 60% is required for passing percentage. 80% of attendance and 60% of score. Test link is now enabled. Participants, you can start with the test. After finishing the test, we request all participants to wait for the valedictory. Thank you, Devraj sir. You may wait for the valedictory function, sir. Participants, those who have completed your test, kindly wait for 5 more minutes. Thank you, Bhaskar sir. Sendil sir, you can find the attendance link, sorry, test link. Dear participants, you are requested to kindly wait for 15 more minutes for the completion of valedictory. Once if you have completed the test, kindly wait for the valedictory function. Sushil, you will have time limit for the test, 20 minutes for the entire test session. Timestamp of all the forms will be considered. I kindly request the participants to share your feedback online. If you wish to give us your feedback, you may unmute yourself and you may share it. Participants, those who have completed the test, may share your feedback.
Hello, ma'am.
Yes, sir.
Myself, Devjit Dash. I'm a junior research fellow of IIST Shibpur. Thank you all the organizing team for considering such an awesome and informative STTP. Well, really lucky to be a part of it. And please inform us if you have any plan regarding conducting any future STTP projects.
Thank you so
Thank
much.
you.
Yeah, thank you so much, sir. We are happy to hear from you, and surely we will inform about the upcoming events.
Thank you, madam. Thank you.
Thank you, sir. If any other participant wishes to give your feedback, you are welcome. Participants, we are going to close the response form for test. If somebody is still doing with the test, we kindly request you to complete it fast. If there is any network issue, you can ping in chat box so that we will give you time.
Madam, some time required. Madam, some time required.
Amarnath sir, okay sir, we will give you time. Welcome participants to the valedictory function. On behalf of everyone, may I request Ms. S. Kripa, coordinator of this STTP Series 3, to propose the vote of thanks. Over to you, Kripa.
Thank you, ma'am. So it's time to propose vote of thanks. It's a great honor to propose the vote of thanks to all who have helped us in making this AICTE-sponsored STTP a resounding success. Firstly, it's my pleasure to extend my heartfelt thanks to our secretary and correspondent, Dr. S.D. Chandrasekhar sir, for being a moral support in all our activities. I also thank AICTE for sponsoring this STTP. I express my profound gratitude to our principal, Dr. M. Jayaraman sir, for his support in making this STTP a successful one. I would also like to thank our beloved HOD, Dr. V.K. Malavanasundaram sir, for his moral support and guidance. I thank our resource persons for giving excellent sessions besides their busy schedule. You're really enlightened with their knowledge and presence. My heartfelt thanks to all participants of this STTP for taking out your schedule and joining with us. And also I wish to extend my deep sense of appreciation for your eagerness in engaging yourself in this particular AICTE STTP. Together, we made it to be a successful event. Thank you all once again.
Thank you, Kripa. Participants, thank you all. We shall end the session. Thank you very much for your participation and patience, waitness throughout these sessions. Thank you all.
So thank you participants for your kind cooperation, and now we are ending the meeting.